Thank you for the opportunity to talk with you today. Being mostly retired and teaching geology as an adjunct Oregon Coast Community College, I don't often have the opportunity to speak with fellow geologists. So, I am very excited to present this overview of my work on a predictive modeling of back beach erosion at Beverly and Moolack Beach, Oregon. This study addresses the critical need to predict back beach erosion at Beverly Beach and Moolack Beach, situated between Yaquina Head to the south and Devil's Punchbowl to the north, a few kilometers north of Newport, Oregon. To meet this need, we developed a robust mathematical model using real-world data from the National Ocean and Atmospheric Administration, or NOAA, and the National Buoy Data Center, NBDC. This view is the study area looking south from Otter Crest along Beverly and Moolack Beaches to Yaquina Head. The study area is approximately 8 kilometers of arcuate sandy beaches protected by the headlands at Yaquina Head at Agate Beach to the south and Otter Rock to the north. The northern half of the beach is named Beverly Beach, and the southern half is named Moolack Beach. The beach experiences a mean tidal range of 2.5 meters, ranging from a negative 1.356 meter mean low water to a positive 1.144 meter mean high water or tide. The tide data is based on mean sea level measurements collected between 1983 and 2001, measured at the NOAA station located at South Beach, Oregon. The northern beaches are wide and sandy, while the lower third features narrow sandy areas and wave-cut platforms. The beaches near Highway 101 are in close proximity to homes and businesses situated on terraces above the back beach sea cliffs. This geographical arrangement highlights the need for a reliable forecasting tool. The coastline in this area is susceptible to mass movements, including circular slumps and rock falls. These natural events pose continuous safety risks to the highway, residential areas, and businesses. The scarp from circular slumps visible in the left photograph occur in Pleistocene terrace deposits. Rock falls, often accompanied by soil and terrace debris, occur mostly in the Astoria Formation. 4 major active slumps directly impact Highway 101 along the northern half of the beach. Because of the danger of catastrophic damage due to the erosion of sea cliffs occurring on the back beaches at Beverly and Moolack Beaches, and indeed along most of the west coast of the United States, a model was designed that would compute the amount of erosion occurring at the intersections of the back beach and the back beach escarpment due to sea level rise, high tide, and swash. This is a simplified flow chart for the back beach erosion model. The next portion of the talk will discuss the inputs, the formulas used in the model algorithm, the model output, and finally model validation. There are 2 sets of input data: constant input data and variable input data. Constant input data provides foundational context to the model, while variable input data captures dynamic changes within the model. Both types of features play crucial roles in building accurate and robust models. The next 4 slides we will discuss input data. The NOAA link shown in the figure provides the data for the maximum sea level rise since 2000 for any coastal community in the United States. The graph represents the maximum sea level rise per year from 2000 to 2100. It provides crucial information for long-term projects and structures. For structures with long lifespans, for example, homes and roadways, or critical functions, power plants, ports, hospitals, NOAA recommends using the maximum sea level rise scenarios. Using the polynomial equation, we determine the annual maximum sea level rise for Lincoln County. This model subroutine computes elevations at the study's beginning and end. The difference between model periods, DIFF, calculates the sea level rise for specific years, for example, 2025 minus 2024. Daily difference, DD, is derived by dividing the annual difference by 730, a number of high tides per year. The modeled calculations are shown in the slide using the polynomial equation shown in the graph for the year 2024. The Astoria Formation outcrop shown in this photo pinches out at Yaquina Head at the southern end of our study area. Rocks assigned to the Astoria Formation characteristically consist of yellow to gray, massive to cross-bedded, medium to fine-grained, feldspathic, locally tufaceous or micaceous sandstone interbedded with varying amounts of silty shale. The rock affected in the study area is a silty mudstone. We used an estimated uniaxial compressive strength of 12.5 megapascals or 1,274,650, about 1.27 million kilograms per cubic meter. This information is sourced from Table 4-3 of the National Engineering Handbook's Engineering Classification of Rock Materials. NBDC data from buoy number 46050, Stonewall Bank, was used to determine the average water temperature for the area for the year 2023. The mean water temperature was 12.09 degrees centigrade. The estimated water density from the temperature salinity diagram for that temperature is about 1.0255 grams per cubic centimeter, which is equivalent to 1,025.5 kilograms per cubic meter. The profiles for each validation site were based on Google Earth 1985 datum and adjusted according to the location and time of the tide line, the beach slope, the distance to tide line, the height of tide at that time, the swell height computation, and sea level rise calculations. The average percentage beach slope is 1.39%. The actual erosion pin elevation at each site used for model validation presented later in the talk was always above the slope intersection with the back beach sea cliff. For example, the intersection of beach slope with cliff face was 4.0 meters, while the erosion pin was set at 4.12 meters. Gravity is slightly weaker at the equator compared to the poles due to the Earth's shape and rotation. Therefore, force of gravity varies with latitude and increases from about 9.78 meters per second squared at the equator to about 9.832 meters per second squared at the poles. The study area is at latitude 44 degrees 43 minutes 25 seconds north, and the force of gravity used in the model is about 9.806 meters per second squared. Next, the average wave period, APD, and high tide, HT, data per day are the variable input data sets. The APD is measured in seconds for all waves during a 20-minute period and presented by NBDC in 6-minute intervals for every hour. Then for the model, the average daily APD data is used. The APD data is derived from the Stonewall Bank Buoy Station located 37 kilometers west of Newport, Oregon. On the central coast of Oregon, we have semi-diurnal mixed tides, and only the high tides affect the model. At the South Beach Tide Station, we generally have 2 high tides daily. This is a massive amount of data that must be cleaned and processed for the model input. It is hand processed on the Excel model and will be automated when converted to Python. An example of the clean data is shown on the right in the slide. The formulas for the model algorithm have been separated into 5 separate oceanic morphological zones for this discussion. intercontinental shelf, near-shore zone, surf zone, swash zone, and back beach. The only deep water information needed is wavelength. The wavelength, LD, is calculated from the empirical formula shown. APD is the average time required for the wave crest at point A to reach point B. The formula is used as we transition through the near-shore zone to the surf zone to determine shallow water wave depth. As the swell approaches the surf zone and transitions from deep water to the surf zone, the shallow water wave depth, S subset D, is calculated using Formula 2. S subset D is equal to LD divided by 20. Deep water wavelength, LD, was obtained from Formula 1 on the previous slide. The shallow water wavelength, L subset S, is calculated from using Formula 3. The celerity or velocity of the C of the breaking wave is given in Formula 4, and the breaking wave height, H subset B, is derived from Formula 5. The results from the preceding formulas are used in the next set of formulas used to model wave action in the swash zone. Once the wave breaks, the depth of the swash zone Z is determined from Formula 6. Then the cumulative predicted sea level rise for each high tide cycle is computed for the study period using Formula 7. Finally, the water height, W subset H, or elevation of water reaching the back beach, which includes swash height, high tide elevation, and the sea level rise, is derived using Formula 8. This is the water that may affect the sea cliffs in the back beach. To determine the surf that will impact the back beach sea cliff or outcrop, the elevation difference, E subset D, between the water height and the slope intersection with the back beach outcrop is determined using Formula 9. Only positive computed values will impact the escarpment. Then the energy of the power of the surf's impact on the outcrop, EPW, is computed with Formula 10. Finally, the amount of erosion, E, for each daily high tide is computed using Formula 11. The results are in kilograms per meter squared. UCRS used in the formula is the constant input rock strength of the outcrop is in kilograms per cubic meter. When you divide EPW by UCRS, the units balance to meters, giving linear erosion in the outcrop. The photograph was taken during a king tide on Christmas Day in 2022 to illustrate the waves breaking against the back beach sea cliffs. Once the model has been coded into Python, the output for the model will go into an output file and will appear similar to the image shown. All the positive depth of erosion values, E subset D, are summed monthly, yearly, or any time interval needed. The model was validated by setting zinc-coated 20 centimeter steel spikes at 6 locations, approximately 1 kilometer apart along Beverly and Moolack Beaches. Slightly smaller holes were drilled horizontally and vertically into the rock. Then the nails were coated with Gorilla Glue and hammered into the outcrop to minimize fracturing the rock. The pins were set in early January 2024. In addition to the periodic physical measurements obtained at the erosion site, a photograph was taken for further analysis and comparison. It was found that the photographic analysis was more accurate and consistent than field measurements. The ratio shown on the slide was used to determine the amount of erosion. The amount of erosion was measured at each pin location on numerous occasions. The time between measurements varies at each location depending on weather, tides, and accessibility. In some cases, several pins were temporarily inaccessible because they were covered either by sand or rock debris. This slide shows the data acquired and the graph of the data for the 20 measurements obtained from the 6 sites. Measured erosion data is the dependent variable y-axis, and the modeled data is the independent data x-axis. The best fit linear trend line had an R-squared of 0.7488. Overall, the data had a correlation coefficient of 0.865. This indicates a strong positive linear relationship between the measured and modeled data, suggesting that the model is doing a good job of predicting the measured values. This was a self-funded project, and I could not have performed the fieldwork without the assistance of Francis Lombardi, my citizen scientist, associate, and friend. We could improve the validation of the model by 1, acquiring the accurate profiles for slope intersection and elevation of horizontal erosion pins at each site. 2, determine the extent of surface erosion on overall erosion due to wet-dry cycle of the siltstone. And 3, having uniaxial compression tests run on rock samples for each site. The next phase of the model will predict when rockfall should occur. I think that by using the methods discussed, we have more than validated the functionality of this model. Thank you for giving me the opportunity to present this talk to you. Time permitting, I will now respond to any questions you may have. Thank you.